Hawking Radiation by Alexi and Harry.
When a massive star burns through all of its fuel, it begins to collapse. There is so much mass inside the star that gravity pushes it all into a single point called a singularity. The event horizon is the area around a black hole from which not even light can escape the singularity's gravitational pull. Black holes must have a gravitational field in order to stop all of the matter from escaping. However, in order to have a gravitational field, virtual particles, like gravitons and photons, must exist in order to carry the force. Scientists realize that if virtual particles exist, so must real particles, as these particles have to exert a force on a real particle. Scientists have come to the conclusion that particle and antiparticle pairs, electrons and positrons, form at the event horizon of black holes because of the uncertainty principle.
Usually, these particles would annihilate each other.
However, in some scenarios, the gravitational pull is stronger on one particle than on the other, so sometimes one particle gets pulled into the black hole and the other one escapes, which leads to the black hole losing energy and the event horizon getting smaller. This theory suggests that eventually black holes will continuously shrink, and as they get smaller and smaller, more and more particles will be created at the event horizon, which means that eventually black holes will evaporate. Scientists have determined that the time it takes for a black hole to evaporate is 5,120 pi g squared m naught cubed over h bar c to the fourth. G is the gravitational constant, or 6.674 times 10 to the negative 11th meters cubed per kilogram second squared. H bar is Planck's constant over 2 pi, or 1.0546 times 10 to the negative 34th joules. C is the speed of light, which is about 300 million meters per second. And finally, m naught is the initial mass of the black hole. When everything is filled in, this comes out to be 8.4 times 10 to the negative 17th m naught cubed seconds, or m naught cubed times 2.66 times 10 to the negative 24th years. The mass of the Sun is 1.98892 times 10 to the 30th kilograms. This means that a black hole with the same mass as the Sun would take 2.09 times 10 to the 67th years to evaporate. The universe is about 1.375 times 10 to the 10th years old. That means that the black hole with the equivalent mass of the Sun would take 1.52 times 10 to the 57th times longer than the age of the universe to evaporate.
That's 152 followed by 55 zeros.
Since they take so long to evaporate, a large black hole will not suddenly disappear. However, scientists think that tiny black holes may have formed in the early universe.
This has led certain scientists to search for a very large explosion that would probably be the result of a black hole evaporating.
Other scientists have predicted that sonic black holes, which are objects that simulate black holes but use sound, should also emit Hawking radiation as sound waves. Unfortunately, none of this has been proven, but scientists are still searching. When this happens, Stephen Hawking may win the Nobel Prize. Thanks for watching!